Hello, am I audible? Okay. Hello and welcome to Group 4 Doubt Clearance session. Week 4. I'm Shreya, one of the TAs of this course, and today I'll be discussing uh, Week 4 lectures primarily. But before moving on to Week 4 lectures, I'll be brushing over some of the R concepts that were discussed during Week 3 lectures. But even before that, if there is anything that you want me to clarify or any doubts if you have, please you can ask me now. No. All right. So firstly, I'll just let me know if you can see my R screen. Yes. Okay. So in the last class, we learned about two types of sampling techniques, which were SRSWR and SRSWOR. That is simple random sampling with and without replacement, and we did a few problems on mainly the probability of selecting samples, probability of selecting um, an individual unit from a sampling frame, and some sort of MCQs which helped us understand what possible scenarios could each of the sampling techniques solve and be better at, and those kind of things. So before moving on, I am going to show you how we can do this with the help of R. So today the first part of this session would be to show how we can perform sampling in R. So the first function that we are going to learn about is the function called sample. Okay, so sample, this is how the function works. If you can see in this fourth panel, this helps us pick a sample of specified size from the elements of X, either with or without replacement. So suppose I have my X is actually a vector which has numbers stored from 1 to 100, let's say. Okay, so this is my X vector, and let us say that I want to randomly sample 10 elements from this list X. So if I want that, in this case my size parameter over here is actually 10, and so by default the sampling is, if I don't provide this replace thing, by default WOR will be applied. So let us see. So if I write here sample and then I write X and then I specified size, then what do we get? I get 10 random numbers ranging from 1 to 100, and none of them repeat. Okay. If I redo, then I get a different set of numbers. The number of times I run this thing, each time I'm going to get a different set of numbers. And by default, the sampling scheme is without replacement. Now, if I want to perform with replacement sampling technique, then I am going to write sample, then x, then 10, and then replace equal to true. Okay, so let us see what this gives. Here again we are not able to visualize whether this replace equal to true is working or not, but it might work. So let's see. So it worked now. 86, 2, 53, 23, 84, 7, 36, 36. So 36 appeared twice. Okay. So in this case x was a numeric vector. But instead of a numeric vector, we could also have some character vector. So let's say x equal to C, A, B, C, D, something like this. E, F, G, H, I, J. Okay, so I could have a list of alphabets, and let's say I want to pick 4 alphabets at random without replacement. Then I can write sample y size equal to 4. I am explicitly mentioning replace equal to false, even though it's a default thing. So see, once we do that, we get EGCF. Now if I want with replacement, then I could write sample y 4 replace equal to true. Okay, and let's see if we keep this running. At one point we will get this. See here, HF again HB. All right. So this is when I have single vectors. Now sometimes what might happen is that I might have a data frame, and that it is very well possible that I have let's say a data frame of 100 individuals where I have their corresponding information on some variables, let's say XYZ, and I want to select or randomly split that data set into or select a handful of individuals and then get the corresponding variables for that sample that I have selected. So I'm going to show you one such example which can that will help demonstrate how to use the sample function in case of data frames. Now disclaimer, this is not the only way that you can do that. There are definitely other ways, but whatever I'm going to show is one of the ways. Fine, so first we need a data frame. Okay, so I will show, I can create one in R, or I could import. I'm going to show both. Okay, so if I want to create in R, let's say I have 3 variables. Let's say I have y here, and then I have information on their heights, okay, in centimeters. So it could be 151, 166, 172, 188, 165, 165, 178, 177, 159, 170. Okay, so let this be the height distribution or height of 10 individuals corresponding to these 10 names. So I could create df1 as data.frame, and then I could have, I'm going to call the y vector as names, not names, I'm going to rename it later. So I need y and their heights. Okay, so now if I see df1, this y and this is heights. Okay, I'm renaming the first column, so call name df1. This gives the list of call names, but I'm only going to rename the first one. So I subset the first one and I select, let's say, name. Okay, so now if I call df1, this is what it looks like, name and the height. Alright, now what I want to do is I want to select randomly 4 individuals and their corresponding subset. Okay, so subset 4 individuals without replacement randomly. So one way to do that is I select sample df1 dot name. So if I do this, I'm going to get, okay, I should provide number 4, the size. Otherwise, if I don't provide this size, it will just permute the number of elements in a vector. So this is another important thing. If we don't provide the size parameter and just provide sample something, then we are going to get a permutation of that vector that we are supplying. Alright, and if we just let us just check what happens if we provide replace equal to true but not the size parameter, then what happens? Then also same thing, we'll only get total number of we'll get a sample where the size of the sample is actually equal to the total number of elements in the population. Okay, so moving on, so if I want to sample df$1 name and I want 4, so here are those 4 individuals. Now I could keep, in order to subset, let's say this is my random name, I call them as random name, and then I write that subset df equal to df1 such that df1 $name equal, or I shouldn't give equal to because this length df1 $name will have 10 elements and this one, that sample, has 4 elements. So if there is a mismatch in the total number of elements, we shouldn't give equal to because equal to actually performs comparisons between equally sized vectors. Okay, so I am going to give percentage in percentage random name. So this is saying that pick those names which are present in this random name vector. So before this I have to apply a which. Okay, so I'll run one by one and then I'll show what each of these things show. So df1 $name percentage in percentage random name is actually going to give me a true false, showing that so this first element will correspond to the first row in it will correspond to the first item in df1 $name. Okay, so the first one is present in random name, yes, true. Second element, true. Third element, false. Now here I have 10 elements in total. It's easier for me to eyeball and check and tell what is the index of these true returns. But since I won't be able to do that for large data sets, I am using this which function. So which is actually returning the indices where this is true. So if I run this which, I can see I get it's true only at positions 1, 2, 4 and 9. Okay, so df, if I give third bracket and 2 arguments, the first would be the row indices and the second one, if I leave blank, if I give comma and then leave it, it means extract these rows and all columns. So this one is going to give me the subset df is going to give me the 4 randomly selected elements and their heights. Is this okay? All right. So this is fine. Now another important thing, which will be needed for practical purposes is that, see, df1, when I run it, subset df is actually abdi. Now if I rerun this, the entire random sample generation and subset df, then we will see that this df has changed. So now it has become ACHI. If I run it one more time, see, it has become AEGJ. So when we are doing some sort of calculation where I need to select a random sample, and then I want that sample to be fixed for the rest of my code, even though I am designing something, and I need that there will be inevitably errors and bugs in my dataset or in my code. So now to fix that, we need to run a code multiple times. But if every time we run this code the sample changes, then it might happen that you have had some results with a certain set of a certain random sample, and then you are adding more analysis and then rerunning, the original sample changes. Okay, so that would imply starting afresh. So if you don't want that, if you want the generator to generate the same sample again and again, what you need to do is you have got to set a seed. Okay, so if we do set.seed and then we provide some number, let's say 7834, let's say. So then once you run this and then you keep on generating this random sample, it's not going to change. So if I just keep on generating, if I set seed and then generate this thing, so every time I do this, I will only get ADGH. Okay, so if you are doing something and you need to check with others, so what you can do is you can set the same number, the same seed, and then generate the random sample. Okay, this will help ensure that whatever calculations you are doing, the original subset or the sample set remains the same across your different analysis. Okay, so this is another useful thing which you should keep in mind while generating any sort of random samples. Alright, fine. So this was one way to do that. You could also subset in a different format. So let's say if I have the row numbers, so let's say n row will give me the length of the data frame. So if I do n row df1, then I have 10. So I could also do sample 1 to n row of df1, and then the size, let's say 4. And now if this is my random set 2, now I could do a subset df1 equal to df1 such that here I have random set 2, because here I am directly sampling the row indices and their corresponding columns. So subset df1 is actually going to give me 5, 9, 6 and 1. The number of row indices that I have sampled, and in that order. Mind you, if I do this, so if you see subset df, then the original order in which the population was specified, that would remain maintained. So see here, I had given A, B, C, D, E, F, G, H. So in the same order, the samples got generated. But if I'm subsetting using the row indices in this manner, then what is happening, I am going to get it will not remain in the same order as it was there in the population vector. Okay, but it will not matter much. You could just, even if you want to do this and then sort it, that also works fine. So if I have subset df1, and then I could do a sort subset df1 something like this, and then again rearrange something like this. Okay, subset df1 equal to df1 such that which let me just write it as sorted which df1 dot name is in sorted. So again I'm going to get these in order. Okay, just two different ways to do things. And if I am not making up a data set in R, I could just use read.csv if I want to import a comma separated file. That would be filename.csv. I could also do a read.table. By default, this will take input any tab separated file, so that would be filename.txt. And if by default any of your files have a different sort of a separator, then all we need to do is read.csv or table, whatever. I give my file name with the complete path, and then sep equal to the separator that is used in the file, and that's it. Okay, so I'm going to show a quick this thing. So let's say I have let's say here is something that I have a same things, names A1, B1, B2, C3, something like this, and then it goes on and on. Something like this, and I have some information, height, okay, 151, 165, 178, 180. Okay, and I save it as let's say example1, and I save it as a txt file. Okay, I could save this. Let me also save it as a CSV file. So here I could save it as a comma separated values CSV. Okay, and also let me save this as a semicolon separated file. Okay, so this one semicolon this thing. Okay, so this is another. I'll name it as example2. I'll save it as a CSV file. Okay, so example2, since I have saved from here, it will be saved as is. Okay, it will be, even though it will be a CSV file, but the separator will be a semicolon. So let us find out. So here if I go and set my working directory, set wd as the directory that I saved it to. So let's say this is the path. Okay, so read.csv, if I just write example1.csv, I get the separated things. Okay, if I just give example1.txt, then also I get these things. I should mention header equal to true for each of them. Okay, so I get this and this as same thing. Now if I just provide example2 .csv and header equal to true, I'm going to get this. Okay, so in order to read this file properly, I should mention sep equal to semicolon, and now I see that it's read properly in 2 columns. Okay, and then sampling would go on as it would have proceeded. Okay, in a similar fashion. Now apart from this sample function, there is another function which we could use that sort of works in a similar manner, but for that we need a package called sampling. Okay, so if you do library sampling, then the library will be loaded. If you don't have this library, then you should use this command install.packages within quotes sampling, and that is going to download the package and store it in your local library, our library. And then once you load it into the memory, library sampling, so they have this function called srswor. Okay, so here you just need to specify small n and capital N. Small n is the sample size and capital N is the population size. So if I just provide 400, then what does it give? It is going to give me a vector of 100 elements, capital N elements, and wherever I have this one, that is my sample selected. Okay, so this is actually giving the indices. I mean, I could think of it as outputting indices where which show that which of the elements are present or have been selected in my sample. Okay, SRSWOR is this, and SRSWR, if I give 400, then also it will actually show me, instead of 1, I could very well have 2, 3 over here, which would indicate how many times this sampling, this unit has appeared in my sample. Okay, so I'll increase this to a little more, or keep this running until I get okay. If I do SRSWR 50, see, here I get some elements which appear twice or thrice in my sample. But if I do SRSWOR 50, I am never going to get anything apart from zeros and ones. Is it okay? Alright. We will get same total 4 selected from 100. Yes. So, right. So this is what is going to happen. I saw another function which is SRSWOR1, which I have to see what they do. So let's check out. So selection rejection method, I don't know, draws a simple random sampling without replacement using the selection rejection method. Equal probabilities, fixed sample size without replacement. And what does this show? Equal fixed sample size without replacement. Okay, so these SRSWOR and SRSWOR1 are essentially giving the same output, a sample selected without replacement, but using different techniques. So we can go ahead and use either of them. Okay, and then whatever is our sample, wherever I have equal to 1. So if I do have a mapped element, so let's say I am going to select SRSWR Y, the names vector. If I want to select 3 names, or let's say 4 names, okay, I won't be able to do that. So it will only take numeric arguments. So if I have to use this SRSWR explicitly, I should actually have to give either n row of df1 or something like this. So this again is actually giving me positions where the samples have been selected. So now I just have to do subset, or let's say df1 such that this one equal to 1. So which index is equal to 1, and then their corresponding columns. So I get BDGH. Okay, now I am curious as to what happens if I increase this. But why am I getting different numbers each time I run this, even though I've selected SRSWR? That is because this entire thing I have given as equal to 1. So to subset, to see if the same thing appears once or twice, I should give greater than 0. Okay, but even then it's not coming. Here I'm getting only 4. Why is that happening? So what happens if I give not equal to 0? Will I get 5 every time? No, I'm not getting that as well. And I'm not going to get that because when I'm subsetting, if I have 2 elements appearing even in the sample, it will only be reported once. Okay, because this function SRSWR5 enrow-df1 is going to show the frequency, but I am only selecting elements from that vector which has some frequency. So even if that shows as 3, since I am subsetting in this manner, I am only going to get the unique elements. Alright, so this is how what was the use of SRSWR1? Okay, SRSWR1 is the same thing as SRSWOR. So this is also giving me this SRSWR1 400 is also giving me the same thing. If I do a set seed, let me see. Only this one uses some different sampling technique. So if I go here, selection rejection method. So I think we have to go through this technique, this paper, which shows how this sample generation algorithm is carried out. So maybe in the back end, whatever algorithm the software is using to generate the sample, that is a different method, which is named as selection rejection method. So if I go to SRSWOR, then this doesn't give us any paper reference, so this must be done in a certain way. And this algorithm, this one, actually follows the algorithm that is listed in this reference. And so basically the thing is, it is actually giving me a sample without replacement, but the technique that the software is employing to get that sample is different between SRSWR and SRSWR1. That is all I have understood from here without going into the details of this paper. If you are interested, you can just check them out. Is it okay? Alright, thank you. So now I am going to move on to some of the week 4 aspects. Okay, is there anything else that you want me to discuss, or with respect to the R programming about sampling? Well, if not, then I'm going to move on to some of the theoretical aspects. Can you tell me what is the use of set seed function? Okay, set seed function actually tells the software to generate the same sample over and over again. So let's say here, if I do not give, so let me just give a sample. I'm sampling from 1 to 10 and I am sampling 4 units, let's say. Okay, so if I run this without set seed, I am going to get, each time I'm going to get a different set of samples, as you can see from here. Okay, so let me run this. So each time I'm running this, I'm getting a different type of a sample. Now let's say I am doing some sort of a calculation where my workflow is something like this. I am selecting, so I have 10 individuals. Okay, I am selecting 5 at random and I'm administering them with some drug A. Okay, and then to the other 5 I am giving some other drug B. Okay, now let's say I am doing this and now let's say after everything, after some sort of analysis I am doing, I'm checking how their height is changing or how their weight. So let's say I am changing how BMI is changing for them. This is just a hypothetical situation. This doesn't happen in the real world, but just to simulate an incident, I'm telling you. Suppose I'm trying to check how the BMI is changing. Okay, and I fit a scatter plot or something, or some sort of analysis I do. All right, and then it is done and the results are stored let's say something has happened and it's there, results.txt, it's stored. Now next thing, I just want to see that for the same individuals how their BP is changing, blood pressure is changing. Okay, so I need to administer something, a certain group of, let's say, drug C to the same 5 individuals, right? So let's say I am my code is something like this. So here I have a subset equal to random name and something I have generated. Let's say I have generated sample 1 to 10 and then 5. Okay, so this was my original subset. Okay, and till here, let's say at this point of my code, I have the results.txt. Now next, and I have saved the script and everything is done. I've closed it. Now once again, if I open it and then if I have saved this script, let's say, as something, and then I move out of R and then I reopen this, chances are that the variables will get messed up and you will not have the same subset sample stored in memory. So you might need to rerun the entire script again to get to this point. Now if you don't give this set.seed, what will happen is that the analysis that you had obtained earlier with a certain type of sample, that subset is going to change. So if you don't provide set.seed, let's say before closing the script, the selected sample was 65319, and now again after, if you want to add some more lines of code and if you are running it again, then you will see 14839. But whatever results you have, that could be a very time consuming, so some analysis you have done perhaps which took you perhaps 6 or 7 days to get the results, and now you want a different type of analysis on the same set of individuals. So in that case, where you need to have the sample set fixed for a certain number of computations, at that moment you should provide set.seed. So if you just set seed to 1 2 3 4 or something like that, then every time the subset that you generate, and you have to run it together, mind you have to run this and this together. So if you do that, every time you are going to run this, you are going to get the same sample. See, 106541. Now suppose you have done something and you are not able to understand what has gone wrong, and you want your peer or your friend to replicate the same sort of analysis to understand where you have done some mistake. Let's say, suppose you have written a function which calculates something and there's a logical error that you're not able to understand, and you need the help of a friend, so you're seeking help. Now that person needs to replicate whatever you have done. So if in your system you have given sample 110.5, the number that you will get, and if in my system I give this sample 1 to 10.5, the sample that I'm going to get, those will be very different. So I won't be able to replicate your results, right? But if you and I set the same seed, then our samples will also remain same. You can very well check it out. If you do it, yes, you can give any random number in set.seed. So let's say if you tell me a number that you have put and the sample that you have received. 5, 6, 7, 8. So 5, 6, 7, 8 and sample 1 to 10. Did you receive this? 4, 5, 10, 1, 7. Okay. So this greatly helps in case of replicating your results. Alright. Anything else? Okay. Fine. Then I'm going to move on to the theoretical aspects. Before moving on to the theoretical aspects, is there anything about previous lectures, previous assignments, anything at all where you need some sort of clarification? What was the date to submit the assignment? Which assignment are you talking about? Week 3 or week 4? Week 3. Week 3 was due on 12th February and today is 15th. So week 3 due dates have passed. Week 4, it's it's on 19th. Alright. So yes, we learnt about this thing. Okay, I did not discuss about sample.int. Sample.int is the same thing as sample, but it will only take the integer values. So sample.int, let's check out. What does this do? So for sample.int, both n and size must be integers. So if I only use samples, I could pass integer vectors, character vectors, anything. But if I want sample.int, I just have to pass 1 to 10 and then no, I shouldn't pass the vector itself. I have to pass the number of integers I want to sample from. So sample.int will give me this. Okay, I need to pass. It's very similar to SRSWR and SRSWOR, but instead of outputting all n elements and showing us whether they are included in the sample or not, sample.int actually provides the numbers that are included in my sample. That is the difference. Fine. Okay. So with that, we also during week 4 lectures learnt about the expectations and variance in so we learnt about the SRSWR and SRSWOR, the expectations, variances and standard errors. So capital Y would be, and we also learnt about some of the terminologies. So I'm going to brush up on the terminologies and then move on to a few problems. Okay, so Y, capital Y, wherever you see, that would be indicative of the population units. So Y is at Y1, Y2 to Y capital N. These are actually my population units. Okay, and if I am selecting a sample of size n, then y1, small y2 and small yn is actually my sample of size n. Okay, and what have we learned about this population and sample? So here the goal is to infer something about the population. So let's say this is my entire giant pool of population and I am studying some quality about this population. Okay, and it is difficult for me to go ahead and check that qualitative or quantitative thing about the population by querying each and every unit of that population. So my goal is to select a subset which would be representative of this population, make my perform calculations and study this sample and then infer about the population based on the sample. Okay, so usually what is the trait or quality that we are interested in? So most often than not, we are interested in the population mean. So let's say I am interested in average height of Indians. Okay, so if I want to infer average height of Indians, it's a humongous task. If I have to go and query each and every individual who's an Indian and ask them their height, and then I have to ask 1 to, let's say, crores of people, n is very very large, and then I have to select 1 by n capital I equal to 1 to capital N yi. So this is actually my population mean, that is y bar. Okay, but I am not able to do this because of constraints in cost, time, etc, etc. So what I am doing instead, so what I am doing instead is I am collecting. Sir, can you please mute yourself? Thank you. Okay, so what I am doing is I am selecting a small sample y1 y2, yn, and if I take the mean of this sample I equal to 1 to n, then this is my sample mean. Okay, and I want to say that is y bar a good approximation for capital Y bar? This is what I want to say, and this is what I want to infer. Okay, now turns out that for both of these schemes, SRSWR and SRSWOR, Y bar is unbiased for Y bar. Okay, so if something is unbiased, this is a good statistical property. Okay, so what does unbiasedness mean? Unbiasedness means that, let's say I have a large population, okay, y1 to yn. Now I am selecting so this is Y bar, let's say, and I am selecting a sample of size n. Okay, so how many number of samples of size n can I select from a population of size capital N? I could select total NCN samples. Do you agree with me? Yes. So I can select a total of NCN samples. Now if I list out all the samples, so L1, L2, LNCN, okay, and then I calculate the Y bar of these lists and then the Y bar of LNCN. Okay, and if I take an average of this column, okay, if I take an average or mean, then I will be very close to the actual population mean. This is what I mean by unbiasedness. That is, if I have drawn all possible subsets of small n from capital N, and then the mean of each of these samples, if I take an average, that would be very, very close to my population average. So if something like this happens, what I am essentially trying to say is that whatever I infer from my sample is actually a good measure of the actual population that we have. And this is exactly what we call as unbiased. In terms of statistical terms, it means that expectation of Y bar equal to capital Y bar. Okay, or we also often call it as mu. In the sense that the distribution of Y bar, if I plot this, so if Y has a distribution, let's say like this is the true Y, and this is the mean, actual mu, and I have certain distribution of Y bar, something here, okay, and then the average of y bar is something here, let's say. Okay, so this is y bar average, and this one is, let's say, equal to mu, or in practical terms, if this is mu, this should be as close to mu as possible, such that their difference actually reduces. So this is what conceptually I mean by unbiasedness. Now, it has been shown in class that this arithmetic mean is a good measure of population mean for both SRSWR and SRSWOR cases. Okay. And then what did we get? Again, another important criteria that we discussed was this thing, that the population variance is also something that is of interest to us. So let's say this is my population highlighted in red, and this is the distribution where I know this is the mean. Okay, and this spread is actually some measure of spread is actually the spread or dispersion. One of the measures is actually variance. Okay, how much the variation is there in a distribution. Okay, so we are both interested in mu and sigma square, because if a certain thing has greater variance, estimates are going to fluctuate. Like, ideally I would want something which has a certain type of population variance, population mean. And I mean, what I mean to say is that for an estimator, I would like to have a certain estimator which closely approximates the population mean and is not too much dispersed, doesn't have too much of variance. Okay, so if there is a lot of variation in the data, then it gets a little difficult to sometimes pinpoint or something like that. Okay, so for example, if I see let me consider this height example only. So if I see that average Indians have a height of, let's say, 170 centimeter or something like that. So if my variation in the dataset is too high, then the confidence with which I can say that an average individual has a height of that many centimeters, that confidence is going to decrease, because I would have a vast range. Like, it could range from 155 to, let's say, 180 or something like that. So, but if the entire variation of the data set is very small, in the sense that it's constrained around the mean value or something like that, then if let's say it ranges between 160 to 172, okay, that is my range. So if I say 170, in that context I will have more what do I call it, I will have more confidence in reporting that number. Okay, so these two are very important criteria for any distribution. So ideally we would like to look at the mean, the measure of central tendency, and the measure of variance. Okay. Now, in terms of sample survey and population, the population part is fixed. I don't have any control on the distribution of the population. This mu is also fixed and unknown in most cases, and the spread is also sort of fixed, and this is also unknown. Okay, so I need to find out some estimate of the mu of the mean, which I am denoting as mu hat, and variance is denoted by sigma square. So I also need some estimate of the variation in the data, and these estimates I am going to collect from the sample that I have. Okay, and then I am saying that whether these estimators that I am going to devise from the sample, whether they have some good statistical properties, in the sense that whether or not they are unbiased for these true unknown parameters. Okay, so we saw here that sample mean for both the sampling schemes, y bar is unbiased for the population mean, that is capital Y bar, or you could say mu. Okay, and we also saw that population variance for SRSWR and SRSWOR which one is unbiased for what. Okay, so here actually we saw that I'm going to introduce the terminologies and then explain in greater detail. So we learned about the population mean and we learned about the sample mean. We also know that variance is actually given by 1 by n summation I equal to 1 to n capital Yi minus y bar whole square. Okay, this is a measure of the population variance. And we also learned about a different term which we mentioned as expectation of S square, and that is actually 1 by n minus 1 summation yi minus y bar whole square. Okay, so both these quantities are actually population based. Okay, and the one that is actually that actually we can calculate is small s square, which was 1 by n minus 1 summation yi minus y bar whole square. All right, now where did these come from? Now I was talking about in this slide I was talking about the spread of the entire data set. Okay, what I'm going to discuss right now will be focusing on this part. Okay, the estimation of mean. This is my primary focus. Now when I'm talking in terms of distribution of mean, so this is my focus here, estimation of population mean. So if this is my population of interest, let's say here is my population mean y bar. Okay, and from, let's say this is my sample or something, and I am saying that this point, let's say here I have my sample mean or something like this. Now mind you, this sample mean y bar is also a statistic. So what I'm saying is that this quantity, since it is also based on different samples, this one will also have some inherent variation. Okay, so what I mean to say is that I am not, whenever I am doing some sampling, I am not collecting capital NCN samples to estimate the population mean. That is something that I told you to explain what does unbiasedness mean. But practically what I am doing, I am selecting just one sample, let's say, from the entire population, making my guess about the population parameter from that one sample. So what I am trying to say here is that I need to ensure that whatever sample I am taking and whatever sample mean I am reporting, that I am reporting with a low what I mean to say is that the variance of this estimator should be low. Okay, and where is this variance coming from? This variance is coming from the fact that if I take a sample, whatever y bar I am going to get, if you take a sample, the y bar that you are going to get will be mostly different. So I need to ensure that this variation is quantified. That is, how much of a difference would it make if I collect a sample and somebody else collects a sample. So if I see, so for every estimator that we have or every statistic that we have, those will also have a certain type of variance, and we need to quantify that because we need that estimator to have a low variance. So if you have selected a sample and I have selected a sample with the same sampling scheme, let's say SRSWR and SRSWOR, if you have a statistic which is so let's say our y bars are same, but variation of y bar in your data set is lower than in my data set, I would be inclined to work with the values that you have calculated, because that is what we want inherently in an estimate. I want this y bar to be as close to y bar as capital Y bar as possible, and I don't want this y bar to have too much of variation. Okay, too much of variation is bad for me. I just want this y bar to be very close to capital Y bar and as close to capital Y bar as possible, and not much of a variation. So for that reason, even we need to quantify two things, that is expectation of y bar, which we have shown is close to, that is exactly equal to capital Y bar theoretically, and we also need to quantify the variance of y bar, that is the variance of the sample mean. Okay, so if the scheme is without replacement, if the scheme is SRSWOR, then variance of y bar WOR is actually expectation of y bar minus capital Y bar whole square, which boils down to n minus n by capital N into capital S square. Okay, and so this happens in case of SRSWOR, and in case of SRSWR, variance of y bar cap WR is actually n minus 1 by n capital S square, where capital S square is this thing. Okay, very similar to sigma square, the original population variance, but with a denominator of 1 by n minus 1. Okay, but mind you, the denominator is 1 by n minus 1, but summation will be from I equal to 1 to capital N. Okay, this will not become n minus 1. So we have seen in the lectures that this is what happens when we have SRSWR, then the variation of this sample mean is quantified by this sort of term. Now this is all good theoretically, but this capital S square is also based on population units. So we need to have an estimate of capital S square as well, so that we can give an estimate of the variance of my sample mean. Okay, so variance of sample mean theoretically will be these, but if we need an estimate for the variance of sample means, we need to have an estimate of S square. Okay, and that is quantified by so this is SRSWR, and let's say this is SRSWOR. So here variance of y bar WR is actually n minus 1 by n SS square, and this is variance of y bar WOR is actually n minus n by capital N into small n S square. But if I want an estimate of the variance, I am going to put this y bar WR cap. So an estimate of the variance of the estimator. So it might sound a little confusing, but this quantity is actually telling us theoretically, if I have a sample, what should be the variation of that sample. Now this hat is telling me how much is the calculated variation of that sample, of that estimator, what is the numerical value. So S, plain and simple, capital S square, since it's based on population units, it's not going to give me the estimate. The estimate is will be given by the small s square values. So what do we get here? So here we see that variance of y bar WR hat is actually small s square by n. Okay, where small s square is how much? 1 by n minus 1 summation I equal to 1 to small n, small I, small yi minus small y bar whole square. Okay, and this one, variance of small y bar WOR, and that estimate is actually capital N minus n by n s square. Okay, so if I have a sample, then I can easily calculate y bar WR or y bar WOR. That will be plain and simple arithmetic mean. And then if I want an estimate of the variance of y bar, then I can also calculate these small s squares from my sample, because I know y bar, I know small y bar, I know small I, small yi's, and then I just need to calculate s square by n or n minus n by this one, capital N into small n s square, and that is going to give me my sample mean and mean variance of sample mean. Okay, and if I want to have, or if I want to quantify the population variance, then so now what I'm talking about is the main population variance. So this is mu, and this, let's say this spread is somewhat quantified by this population parameter sigma. So if I want an estimate of sigma square, then I could say that for SRS WR, S square is a good estimate of sigma square. Okay, so if somebody wants to say that give me an estimate of the population variance, then I am going to report small s square. Okay, and if if I'm having SRSWOR scheme, then I will see that small s square is actually good for or unbiased for capital S square. Okay, so again, if you see, capital S square is actually n by capital N minus 1 into sigma square. Okay, because sigma square has denominator n and capital S square has denominator n minus 1. And we see that expectation of small s square is equal to capital S square. Okay, so from here, if we just do a little bit of tweaking here and there, then we can see that expectation of n minus 1 by n into s square is actually giving me sigma square. So if I am reporting small s square, then that is unbiased for capital S square. But if I need a good estimate of sigma square, the population variance, then I just need to adjust it with the n minus 1 by n factor, and this entire quantity will actually then be a good estimate of the population variance. Okay, in these things. Alright, and we also learned that which of the two sampling schemes are actually better. So what we see is that SRSWOR scheme performs better in case of estimation of mean. Okay, so here, if we are quantifying the variance of y bar WR and variance of y bar WOR, then we see that this variance is actually greater than this thing, because this one was what? This was n minus n, sorry, this was n minus 1 by capital N S square. Okay, so this one I can write as n minus n plus n minus 1 by n S square. So this would be n minus n by n S square plus n minus 1 S square by n. And this one is a squared term which is positive. Small n is greater than 1, so it is positive, and this is also positive. So this entire quantity is a positive term. So what we have is variance of y bar with replacement is greater than variance of y bar without replacement. So if somebody, now here comes the question of low variance that I was saying. If you have a sample and the technique you have used is actually with replacement, your estimator is going to have a lot more variation than the estimator that I have chosen, and that is based on the without replacement scheme. Okay, so variance should be small as possible. So when it comes to increased efficiency, then any day this without replacement scheme is actually preferred. when we are talking about estimation of population mean. Okay, so this is uh, what is needed. Now this is variance of population mean. Okay, now if I want to talk about this term, variance of y by wr, or root over positive root of y bar wor, then these quantities are actually what I call as standard errors. Okay, so usually whenever we put out any sort of estimate, we usually report. So reporting, not mandates, reporting practices, I would say, is whenever we have some statistic, we report the realized value of the statistic and the standard error. So here my statistic of choice is y bar, because it's purely based on the sample. Why am I calling it a statistic? Because it's purely based on the sample and there is no unknown parameter involved over here. Given a sample, I can compute this thing with only the sample values and nothing else. I don't have any unknown parameter in the expression of this y bar. So this is a statistic, and whenever I am doing any sort of sampling, I am going to report the realized value of the statistic, that is whatever I've observed from the data, and the standard error associated. The standard error is actually root over variance of y bar wr, or root over variance of y bar wor. Now since we have seen that these variance expressions also depend on population terms, we are going to report the root over of that v of y bar hat, whatever I showed, that can be computed from the sample. Okay, now one more thing that we should be very careful about is that even if we, so for reporting sake, we are going to report root over variance hat, variance of y bar wor hat, or root over variance of y bar wr hat, but this will not have the good properties as of the this. Okay, so root over this one, variance hat of y bar, this is actually, this will have some what do I say, this will have some good properties, will be unbiased for some quantity, but that doesn't imply that root over this entire thing is unbiased for root over variance of y hat. Okay, so be very mindful about this fact. Whatever expression you see over here, if the inner part is actually good for some estimator theta, root over this inner part will not be good for root over that theta. This one-to-one mapping doesn't work in real life. Okay, so this is also something that we should be very mindful of. Okay, so these were the things that we discussed in group 4 lectures. I'm going to just briefly go over a small section which will help us with the assignment questions. So if I have this question, that suppose a population consists of 6 units, these with these measurements, write all possible samples of size 2 by without replacement from the population and verify sample mean is unbiased estimate of the population. Okay, so sample mean is unbiased estimate of the population. How am I going to, so population mean is how much? Y bar is actually 2 plus 6 plus 8 plus 10 plus 12. 1 2 plus 4, I missed 4, okay, by 6. So this is the population mean. Now write down all possible samples of size 2. How many samples of size 2 can you select? There will be 6 C2 samples. Okay, that would be 6 factorial by 2 factorial into 4 factorial. There will be 15 such samples. So we list out 15 combinations. Okay, so it will be 2 4, 2 6, 2 8, 2 10, 2 12, then 4 6, 4 8, 4 10, 4 12, then 8 10, 8 12, and then again how many do we have? 10 12. So how many are we getting? Are we getting 15? 1 2 3 4 5 6 7 8 9 10 11 12. I'm missing something, I think. 2 4 2 6 then 4 6 4 8 4 10 4 12. Okay, I missed the 6 8 part. 6 8 6 10 6 12. So I have 15 samples. So I just calculate these. So 2 plus 4 by 2 is actually how much? That is, from this sample I'm going to get 3. From this sample I'm going to get 4. From this sample I'm going to get 5. And then if we take all these samples and take an average of this thing, we'll have to check whether that average matches with the population average or not. Okay, then only we'll be able to satisfy option A. And then sample mean square is unbiased estimate of the population mean square. Same thing, we calculate the population mean square and then the sample mean square and check if they are unbiased or not. Okay, and we also calculate sampling variance of the estimate, sample mean, and verify with the formula of variance, and find SRSWR is efficient than SRSWR and find the gain in efficiency. So sampling variance of estimate means we have to calculate variance of Y bar hat. Okay, and then we have to see whether this thing is matching with the population one or not. So since this is without replacement, if we, for each of these samples, if we calculate small s square, so for 2 4 2 6, everyone will have a small s square, right? And then if we take an average of this thing, we'll have to check whether that average is equal to capital S square or not, which is 1 by n minus 1 summation yi minus y bar whole square. Okay, so long things, if I just have to summarize, then y bar, expectation of y bar WR equal to expectation of y bar WOR, which is equal to capital Y bar. Okay, and expectation of small s square is equal to capital S square for WOR, and this is equal to sigma square for WR. Okay, and if we want the variance of y bar WR, then this is actually, the estimate of this is actually n minus 1 by n into small s square. Sorry, this is not the thing. This is what did I write down here for this thing?
S square by n, ma'am.
Yes, s square by n, and this one will be n minus n by n s square. Okay, and if I just want to report the standard errors, then I have to report root over variance of y bar WR hat or root over variance of y bar WOR hat. Now for the assignment questions again, if you have some sort of sampling technique given and you have to compare the ratio of variances, then just write down the formula of the variance and then putting the appropriate numbers and sample sizes, just get the ratios. Be mindful what they are asking about. If they, whether they are asking about variance of y bar or variance of y bar hat, this is something that you need to be mindful about. Okay, based on the how they are phrasing the question. All right, is there anything that I should discuss further? Please let me know if you have any doubts. All right, then I'm going to end today's session. Thank you very much for joining, and if you have any doubts, you can put it up in the discussion forum if you want, or join in the next session to get that clarified. All right, thank you so much and have a good day. Thank you.